Hello.
Oh, hello.
Hi, welcome on stage. It's great to have you,
Oh,
Tina.
yes. It's really nice that you invite me as a speaker today. So, yeah.
No pleasure. We look forward to your presentation. So I think you have about 20 minutes in total. If we think you're overrunning, we'll intervene. Otherwise, yeah, I wish you good luck. And again, to the audience, please ask questions. It's really awesome to hear questions from you.
Okay.
So good luck,
So,
Tina. You can start.
okay. So, thank you for attending my presentation. My name is Zixuan Zhao, but you can just call me Tina. It will be easier for all of us. Now, I'm an RD engineer in Taiwan Perovskite Solar Corporation. We are dedicating ourselves to pushing perovskite solar cell toward commercialization. Therefore, I have some experiences of large-scale production in perovskite solar cells. That's also my topic today: large-scale perovskite production, materials, processes, and challenges. So, for those who are not familiar with perovskite, I'm going to give a concise definition here. Perovskite is a crystal group sharing similar crystal structure with calcium titanate. This crystal structure is also shown in the logo of my company. Of course, we don't use calcium, titanium, and oxygen to make solar cell. Usually, we use methylammonium, lead, and iodine. It is possible to replace some ions in this compound. Sometimes it makes solar cell more efficient and stable. And perovskite is a candidate material for next generation solar cell. So far, the highest efficiency has already reached 26% this year in the lab level. It is comparable with silicon solar cell. And it has also other fantastic characteristics. First, it's thin film, so it's flexible. It can be on cars, on airplanes, on curtains. And second, we can adjust band gap of perovskite to changing these ions in the compound. But changing band gap also means changing the transparency. So it can be somehow transparent, but we lose some efficiency simultaneously. Third, it's possible to save the cost in the future because the manufacture process is quite cost effective compared to silicon solar cell. However, it has very big drawbacks. It can be damaged by water vapor, oxygen, and may degrade for over 200 Celsius degrees. And this temperature also puts some limitations on manufacture processes for top layers. So, uh, well, what are top layers? This slide shows two typical perovskite solar cell structures. The main difference between these two structures is the manufacture sequence. In conventional structure, the manufacture sequence is from cathode, then ETL, perovskite, HTL, and anode. In inverted structure, it's totally opposite. From the aspect of theories and functions, these two structures are totally the same, but from the aspect of manufacture, they are very different. So in conventional structure, the characteristic of perovskite constrains the choice of HTL and anode. It's not only the choice of material but also process. And in inverted structure, the same thing happens on ETL and cathode. So the red square circles the top layers. And first, let me talk about how to choose a nice material. So theoretically, we should consider band alignment. Take MAPBI3 for example. Its HOMO is 5.4 eV. Its LUMO is 3.9. So we should choose an HTL whose HOMO is near 5.4 and choose an ETL whose LUMO is close to 3.9. Then we will get a bunch of choices. And if a material is organic,